KC2IRV back again with my little phase lock loop project that I've been working on for the RTCM. As I left you before, I had made a video, kind of a hasty video of the unit I had prototyped and had working on the bench. And now I have the schematic fully drawn. I have it on my computer. I'm kind of filming this with my phone on my computer screen, mainly because I haven't found a screen capture program that wants to work correctly or not crash. So I'm doing it this way. So anyway, this is the schematic. I have it written in Express PCB. And I wanted to kind of go over it a little bit with you. Just kind of giving an overview. And once again, if anybody wants a copy of this, they're more than welcome. So anyway, as you know, this is a phase lock loop circuit to lock 9.6 megahertz oscillator to a 10 megahertz reference. And this is how it accomplishes this. We pretty much have 2 amps here. We have a 10 megahertz reference in that's got to be coming in at about 2.5 volts peak to peak coming in here into this amp. This is a bit of a buffer. This buffers it. And then this amp actually kind of flat tops it a bit. Kind of wave shapes it. Makes it a little more agreeable to the input of the divide by 10 IC here. So anyway, it gets fed into the divide by 10 IC through the clock input B, and from there it divides that down to 10 megahertz down to 1 megahertz, which then feeds the clock input B of another divide by 10, which then divides it down to 100 kilohertz. And from there, as you can see, we have our phase detector, which is nothing more than an exclusive OR gate. It's very, very simple. Aside from that, we have our loop integrator circuit, which basically, I went off the screen, which basically takes the pulse train out of here, which this is then fed after the divide by 10 here. 100 kilohertz goes into the exclusive OR and is then compared. So before we get to the loop integrator, let's go to the other side of the circuit, which contains our 9.6 megahertz OCXO. Now, for a phase lock loop circuit like this, you don't have to have a high stability oscillator like an OCXO. You could use a you need an oscillator that is voltage adjustable, and in this case, it needs to be voltage adjustable in the positive direction, which means the oscillator needs to increase its frequency output with an increase in voltage. Which, I mean, that can easily be, if you have an oscillator that goes in the opposing direction, you can use some inversion circuitry, basically a transistor and a few the small handful of parts to invert that. So I'm just using this 9.6 megahertz OCXO, and the OCXO, what'll happen is if you ever lose lock, this will free run and remain very, very stable, as opposed to, say, a standard crystal oscillator. So this puts out a heck of a lot of signal. So that's why you notice my output is pretty much unbuffered. This cap here is basically a bit of a buffer against the output. I get plenty of output here to drive the RTCM clock. So that gets fed into exactly the same circuit that we're using above. It's the exact same circuit, a carbon copy of it. And that gets fed into the clock B of a divide by 12. Pardon me. Which then takes this 9.6 down to 800 kilohertz. And then that gets fed into a divide by 8, which then takes that down to 100 kilohertz, which we now have 200 kilohertz pulse trains present at the exclusive OR inputs. Now we have a 200 hertz pulse train that comes out of the exclusive OR that goes into this transistor, which acts as a loop integrator. And that gives us, through these resistors and capacitors, gives us a steady DC voltage on the output, which is varied by the pulse width of the pulse train, of the positive pulse width coming out. So that varies this DC voltage. And then that DC voltage is fed to the oscillator controlling its output, creating this line creating our loop, our phase locked loop. And this variable resistor here is used to get our voltage close to the voltage of the OCXO, close to where the OCXO is somewhat in the ballpark of frequency, because you only have so much of a range for pull. I've been setting this point with no input, no 10 megahertz input. When you do that, you only get pulses from the one side, and you get a 50-50 division on the positive and negative going pulse train, positive and negative going portions of the pulse train, I should say. And you can set this. I set this for about 3 volts. That has more than enough pull range to pull just about any one of these oscillators. One of these, the standard ones I've been using, into lock. Pull it on frequency to phase lock it. So that's this part of the schematic. It's not a very complicated circuit. It doesn't have a lot of bells and whistles, like there's no lock indicator or anything like that. That's pretty much I've been doing by reading voltages. Then we have the power supply portion of the circuit, which I'm just using an LM7805 for my 5 volts to my devices, and then an LM1085 for my 12 volts out, which is primarily for my crystal oven. But you need at least 13.5 volts in. Otherwise, the voltage on the output of this regulator begins to drop, and that can cause the output frequency of the oven to vary. So this needs to be above 13.5 volts and under 24, because that's the specifications of the regulator. Other thing that is very, very important in this circuit is, what they call RF bypass caps or decoupling caps. On every IC, I have a 0.01 microfarad cap on the across the power and ground leads of the IC, and that keeps basically RF noise off of the ICs. I actually found that out whenever my furnace in my house would fire up. It would send this circuit bonkers, because the arcing of the starter in my oil furnace would create a whole bunch of RF noise, and then throw the circuit out of lock, and then it'd have to walk its way in again. And on the Motorola one, which is extremely similar, I didn't have that problem, but they also had lots and lots of these caps all over the place. So that is the schematic. What I have now, which I'm going to eventually order, is the board. May not be the most efficient design, but everything fits in a fairly compact package. This board is drawn in Express PCB's CAD software. Unfortunately, Express PCB does not output Gerber files unless you pay for them. So unless you're willing to pay the $60 for the Gerber file, you have to buy it from them. Cost for 2 boards at the moment is going to be about $100. So, which I'm kind of weighing to see if I can get those made any cheaper by possibly getting the Gerber files. But I may just go ahead and do it anyway, just for prototyping purposes. So, and everything's going to be a lot more compact. I put in this large shaded area as a ground plane, and this is mainly for the OCXO output. I don't want to just run as a trace. Oh, I just moved stuff on my schematic. Look at that. I can put it back. There we go. I don't want to have it as a trace, like a long antenna. And I thought about creating a strip line on the board, and I really didn't want to get that complicated with it. So it's just going to be a straight, small piece of RG316 coaxial cable. And what I'm going to do is I'm going to strip the jacket at small intervals and solder it along this ground plane until I need to bring it over here. So that's pretty much the reason for that. But the board is pretty much ready to go, and hopefully this is going to work out well, and I'll probably make more of them. Besides that, I'm going to hopefully, once I get this fully assembled, do a video on that as well, of the completely assembled unit. And this unit should be able to phase lock my RTCMs together and keep the small differences that I'm having between the two sites, which the OCXOs have been working great, but you can tell that they do move around a little bit. They do kind of drift in and out. It's not very noticeable most of the time, so this is going to solve that problem. So these are both, if anybody would like, these with the schematic or the board layout, or if if anybody else comes up with a better board layout, then by all means. This is just my attempt at it. I printed out a couple. This one is before I did the whole. This one is before I did the whole ground plane. So, but nice. It prints it out, and the printout is the actual size. So that's actually how I had to find out. If you look over in the bottom corner here, I had to actually, I had to measure out the spacing for the OCXO and put the pads in the correct places, and having a place to having that paper printout allowed me to place it on the page and make sure it's going to fit when I order the boards, because I don't want to order 2 boards for $100 and then have the device not fit on the board. So got plenty of test points, stuff like that. The other thing I do want to mention is if I look up this, go back to the schematic here. You have a 100 kilohertz, insertion point here on this exclusive OR gate. So what I do want to mention is this. Here we are. Back over here. Put this in front of the camera. You can use one of these. Oh, can't really see it. Let's get my flashlight out. It's a really hooky way of doing this. You can use one of these. The Neo 7M. I don't know if you can see it or not. I don't think I can focus on it. Probably not. But anyway, you can use one of these guys and program the 100 kilohertz output, and use this instead of a 10 megahertz input to lock that and eliminate that entire set of circuitry with this one small GPS device. It means you're going to have to run a second GPS antenna, but it is an option. And it's one I have tested, and it works. Works just as well. So that's it's really a nice option. I may actually create a board that uses that unit and reduces this parts count and actually makes a more compact unit. And that way all you have to do is connect the GPS antenna to it, and off you go. And these units, the Neo 7Ms, will drive an active antenna. You get about 3.5 volts out from the connector to drive an active antenna. So it's for, I think they're $14, $15 a piece. The connector on it, I put an SMA connector on it. Or cheap. It actually has a spot for board mounting, edge mounting, and an SMA connector. So that's it for now. Not a very exciting video, but hopefully informative. Like I said, if anybody has any questions, comments, there's the comments section, but I would encourage you to email me. I don't always get back in the most timely manner, just because I've been very, very busy at work at the moment, but I will try to get back to you. And if anybody wants a copy of the schematic, I can give you a PDF copy, or I can give you the copy I have in the Express PCB format. So that's all for now, and I'll catch you guys later.